Hey guys, welcome to Crown Smart. In this video, we want to show that not every algebra is a sigma algebra. Now, in my previous video, I showed that every sigma algebra is an algebra, but the converse is not actually true, right? Now, for me to show that every sigma algebra is an algebra, I need to show that it is sufficient enough to show that the third property of an algebra holds. Okay, we need to show the third property. Okay, so the third property says that if A and B is an element in the sigma algebra, then the finite union is in this sigma algebra, right? So if I can show that this holds in a sigma algebra, then definitely this sigma algebra is what? An algebra. So now, of course, since this is a sigma algebra, it means that there exists a sequence n equal to 1 to infinity as a subset of what? This sigma algebra, such that the countable union n equal to 1 to infinity of that en is in what? This sigma algebra. Okay, but the union n equal to 1 to infinity of en is equal to E1 union the union En n equal to 2 to what? Infinity. So if I set A to be E1 and I set B to be the union n equal to 2 to infinity of En, observe that A is okay, such that this is in what? En. So if we do if we now look at this union again, so therefore the union n equal to 1 to infinity of En is equal to E1 union this, right? E1 union the union infinity of En. So this gives me what? My A. Since my E1 is A union, then this will be my what? B. Okay, now of course the union of this will actually give you a set. We call that set B. So we've shown that A union B is in what? Is in this A. So definitely this means that every what? Sigma algebra is an algebra. Now let's go back to the main business. The main business is to show that not every algebra is a sigma algebra. So recall that in my also last video I showed an example of I showed that this actually, look at this algebra, let me call it A naught, is the collection of A subset of R such that either A or A complement is what? Finite. So this is an example of an algebra that is not a sigma algebra. So in my previous video, I actually showed that this is an algebra. If you go back to my previous video, you will see that I proved that this is an algebra. So but I want to show that this is also what? Not a sigma algebra. This is an algebra but not a sigma algebra. But in this video, actually, I'm going to still prove it, but I'll just make it brief. Okay, I'm going to prove that this is an algebra in this video, but I'll make it brief. But if you need the full proof, you need everything, you need the necessary information to show that this is an algebra, you have to watch my previous video to know how I prove that this is what? An algebra. So to show that this is an algebra, remember, we have to show that it satisfies 3 conditions. So the first condition is that the empty set must be in what? In this algebra. And this is true. Reason is because the empty set is in this algebra because for anything to be in this algebra, either that element is finite or its complement is what? Finite. And of course the empty set is finite. So this implies that the empty set is in what? The algebra. So secondly, we said that if A is in this algebra, then its complement must also be in what? This algebra. But of course, A in this algebra implies that A is finite or A complement is finite. Okay, so which of course we can write as A complement is finite or A is what? Is finite. Okay, so since we can write it that A complement is finite or A is finite, just reverse of it. Instead of, it's just like saying 2 or 3 or 3 or 2. Okay, so this now implies that since we now have A complement is finite or A is finite, we can now conclude that A complement is what? The algebra, because for A complement to be in the algebra, A complement is finite or A is what? Finite. Now the last case, to show that this is an algebra, we have to show that if A and B are in this algebra, then A union B is also what? This implies that A union B is in what? The algebra. We have to show this last case. Now, to show that this last case is true, we have to consider 3 cases or 4 probably. So we have to consider like 4 cases or 3 cases probably. So the first case is if both A and B are what? Finite. That's the first case. The first case is if both A and B are finite. Now, if A and B are finite, then A union B is also finite. Okay, then this implies that A union B is in what? The algebra. Okay, because if A is finite and B is finite, then their union is finite. So it means that this is in what? In the algebra, because for anything to be in the algebra, it must be finite, this must be finite, or its complements must be what? Finite. Now, if I take the second case here, okay, I can take A complement to be finite, or I can take B complement to be finite, whichever one I want to take. But if I do for this one, it's the same thing as doing for the other one. Okay, so if I say A complement is finite and B is finite, so if I solve for this, it's also the same thing as doing B complement is finite and A is finite. Okay, so if I do for this, it's the same thing as doing for this. So if I do A complement is finite, if I say A complement is finite, it means that A is what? Infinite in R, because the complement of if A complement is finite, actually, if A complement is finite, now A complement is going to be what? A, which is going to be what? Infinite. Okay, so which is the same thing as R difference A complement, which is going to be what? Infinite. So the union A union B, that's infinite set union infinite set, will be what? An infinite set. So since it's an infinite set, okay, it means that A union B is not in the algebra. But let's look at the complement of A union B. So if we do the complement of A union B, we have this as A complement intersect B complement. And of course, we know that this intersection is a subset of what? A complement. Okay, since this intersection is a subset of A complement, it means that an A complement is finite. It means that this intersection is what? Finite. So definitely this is what? Finite. Okay, so if this is now finite, what does it mean? It means that A union B is in what? In the algebra, because we say that that union must either be in the algebra or the complement of that union must be what? In the algebra. So please, if you go back to my previous video, please go and watch this. You will now understand how I make this proof. I'm just trying to make this one brief. Okay, so the last case we are going to consider if A complement is finite and B complement is finite. Now, if A complement is finite and B complement is finite, it means that A is infinite and B is infinite. So their union is what? Infinite. But if I take the complement of it, this gives me A complement intersect B complement. This gives me A complement intersect or B complement. And of course, A complement is finite, B complement is finite. Now, the finite intersection of a finite set will give us what? A finite set. And of course, this intersection is finite, so definitely mean that this complement is what? Finite. So in general, we have shown that A union B is in what? This algebra. Now, we have shown that this is an algebra, right? So we need to show that this is not what? A sigma algebra. Now, to show that something is not true, it is sufficient to pick a counter example and show that it is not what? True. So to see this, now, to see this, set an equal to the singleton n, okay, for every n in the set of the natural number. Now observe that an is in what? A naught. Remember, we want to show that this is not a sigma algebra, so we are picking a counter example. To see the set an to be the singleton n for every n in the set of natural number. Now observe that an is in a naught. Okay, an is in a naught for every n in the set of natural number. Now why is an in a naught? This is because an is what? Singleton n. And what is a singleton n? Singleton n is a finite set. The cardinality of it is 1. So since the singleton set is finite, this implies that an is in what? The algebra. Because the algebra says for anything to be in the algebra, it must be finite, or its complement must be what? Finite. So since this singleton set is finite, then an is in what? The algebra. Okay, so since an is a singleton and thus finite. Okay, but okay, so this implies now that the sequence n equal to 1 to infinity is equal to the sequence of this set, this singleton, n equal to 1 to infinity, is a subset of what? A naught. So if an is an element in this, then the sequence of that an, that is, if this an is an element of this, for every n you pick, then this sequence, which is actually this, is a subset of this. That means this is a subset of a naught. Now if this is a subset of a naught, it means we have created a sequence, a countable sequence. It means we have created a countable sequence that is a subset of what? A naught. So since we have created a countable sequence that is a subset of a naught, we need to check if this is what? A sigma algebra. Remember, for you to show that something is a sigma algebra, you have to have a sequence, a countable sequence, subset of that sigma algebra, and then you now show that the countable union is in that what? Sigma algebra. So let's see if the countable union of this will be inside a naught. So we have generated a countable sequence that is a subset of a naught. Let's see if the countable union is a subset of, is an element of this a naught. So let's, okay, so this implies that, okay, let's not use this implies, but the union, the countable union of n equal to 1 to infinity of an is equal to the countable union n equal to 1 to infinity of what? The singleton n. Okay, so this countable union, which is this. Now of course, the countable union of a singleton set of a singleton set n, where n is coming from a set of natural numbers, what will it give you? To give you the whole natural number. So when you take the singleton set where n is coming from a set of natural number, when you do their union, it's like saying this union 2 union 3 union ... This will give us 1 2 3 4 ... and which we know is what? The set of natural numbers. Okay, so this countable union forms the set of natural numbers. So now I want to now show that this is what we want to now check if this set of natural number is in this algebra. Now once we have shown that this set of natural number is in the algebra, then it means that the countable union is in the algebra, and therefore the algebra is what? A sigma algebra. So let's check. Now, is n finite? No, n is an infinite set. So because n is an infinite set, we now check, okay, let's see if its complement is what? Infinite. Let's see if its complement is finite. Remember, for anything to be in A naught, it's either that element is finite or the complement is what? Infinite. So since n is infinite, let's look at n complement. Now look at n complement. N complement is simply what? The set of real numbers without n, right? Now of course, set of real numbers without n, what will this give us? This will give us minus infinity to 1 union, what will this give us? The union n equal to 1 to infinity n plus 1. Okay, this looks cumbersome. Let me break this down. So let me break this down. So let's look at this. Let's draw a set of real numbers. This is actually n infinity, n complement. Okay, so if this is a real number, if this is the real line, now of course the set of natural numbers start from here, 1 2 3 4, and we want to do the complement. The complement is, remember, the set of natural numbers are 1 2 3 4 and so on, right? These circled ones are the natural numbers. Okay, now the complement of the natural number is simply the real line without n, right? So the real line without these numbers, that is the real line without these values, are actually all the shaded parts, all the shaded parts, all the shaded parts, all the shaded parts, and so on. So from here to here is minus infinity to 1. Okay, so from here to here is minus infinity to 1 union. Now if you take the individual, look at this individual part. Look at this. Here is from 1 to 2, here is from 2 to 3, here is from 3 to 4. So remember, this shaded part is the open interval 1 to 2. This shaded part is the open interval 2 to 3. Okay, this shaded part is the open interval 3 to 4. Of course, I can write these open intervals as 1 to 2, 2 to 3. Observe the way I wrote it. So I can either write the open interval like this or like this, 3 to 4, and so on. Okay, and so on. So now if I now take their union, if I now do this union, this union, this union, this, I will now have the union n equal to 1 to infinity. Okay, I will now have n equal to 1 to infinity of n plus 1. Okay, now observe, if n is 1, then n plus 1 is 2. If n is 2, then n plus 1 is 3. If n is 3, then n plus 1 will be what? 4. So if n is 1, n plus 1 will be 2. That's why we have this. So this is like a general representation of these intervals. So that's what I have here. Now observe that this is an infinite set. This interval is an infinite set. This interval too is an infinite set. So the union of an infinite set still forms an infinite set. So this means that n complement is also what? Infinite. Now remember, we said for anything to be in this algebra, for a set to be an element in this algebra, that set must either be finite or its complement must be what? Finite. But n is not finite and n complement is not finite. So this implies that n is not in the algebra. So this now implies that the countable union n equal to 1 to infinity of an is not in the algebra. And since the countable union is not in the algebra, definitely it is not what? A sigma algebra. Because for it to be a sigma algebra, the countable union must be in what? The algebra. So this means that A naught is an algebra but not a what? A sigma algebra. Thank you very much for watching this video. I hope you understood it. Please, if you don't understand, you can go back again and rewatch the video to get the full gist of this. Please don't forget to like and subscribe, and please share to your friends. Thank you.